Hello everyone, my name is Cédric Androuët. I'm working for the Canadian Nuclear Safety Commission, and I'm happy to present you today the results of this project carried out with Jean-Philippe Charron from Polytechnique Montreal regarding the effects of shrinkage reducing admixtures, mixing and curing conditions on the shrinkage of an ultra-high performance fiber reinforced concrete, which we'll call UHPFRC for the rest of the presentation. The presentation will be divided in 4 sections. First, an introduction, then the methodology, followed by results and discussion, and I'll finish with a brief conclusion. Ultra-high performance concrete are materials that present exceptional mechanical durability and rheological properties. Typically, we have a compressive strength higher than 120 MPa, a very low permeability, excellent resistance to scaling, abrasion, freeze-thaw degradation, etc. When we add some fibers to those materials, we obtain ultra-high performance fiber reinforced concrete. And those are very high tensile strength, up to 15 MPa, sometimes more, and a very interesting ductility as well. And typically, those are obtained by reducing the porosity of the material and improving its microstructure. This leads us to the typical composition of a UHPFRC. If we have a look at this table, what is interesting to see is that we have a very low water binder ratio for UHPFRC, as well as quite a high amount of binder. This means that those materials have a high autogenous shrinkage, leading to some risks of cracking, and especially at early age, because the early age shrinkage represents a large part of the long-term shrinkage. So to reduce the early age shrinkage, we have different options. We can use admixtures, shrinkage reducing admixtures, expensive admixtures, etc. And we can control the curing conditions, temperature and relative humidity. So the objectives of this project are to evaluate the effects of different mixing and curing conditions on the shrinkage properties of a UHPFRC, and to evaluate the effects of different SRA on the shrinkage properties of a UHPFRC. For the methodology, we use the UHPC developed at Polytechnique Montreal. It has a water binder ratio of 0.2, 3% volume of steel fibers 13 mm long. We use a polycarboxylate-based superplasticizer so that we can have a self-consolidating behavior, typically a slump flow of 700 mm and a mini slump flow of around 230 mm. This material has a characteristic compressive strength at 28 days of 120 MPa and a characteristic tensile strength at 28 days of 9.5 MPa. For the shrinkage reducing admixtures we use, those are 2 polyol-based materials, and those are the same material. One is supplied in liquid form and the other one is supplied in solid form. So for the SRA1 supplied in liquid form, it would be added after water and admixtures in the mix, while the SRA2 supplied in solid form, it would be added with all the dry materials before water and admixtures are added to the mix. We tested the slump flow of all the materials we poured in this project. We tested as well the mini slump flow, the air content, temperature of the fresh concrete. We measured the temperature with thermocouples as well. We measured the compressive strength, and we will focus in this presentation on the shrinkage of the material. So the shrinkage was measured with these kind of sensors. So basically we install the sensors in the mold, and then we pour the concrete in the mold so that the sensors are completely embedded in the concrete, and it allows us to measure the deformation of the concrete straight when the concrete is poured in the mold. So that's very interesting when we study the early age shrinkage. For the experimental program, we studied the effects of temperature, humidity, and SRA. Because time is limited, we will focus on the humidity and SRA experimental program in this presentation, and I refer you to the paper we wrote for this conference for the effects of the temperature. So we have our reference mix with the mixing temperature at 30 degrees and a relative humidity of 50%. And we studied what happens if we have a relative humidity of 100% and what happens if we immerse completely the specimens in water. At different starting times, we're going to talk about that in a few seconds. And we studied as well the different shrinkage reducing admixtures at a dosage of 2%. When we have a look at the results, we need first to make a distinction between the negative deformation we measure with the sensor and the shrinkage itself. Why? Because we have an impact of the hydration temperature. Here on the left is the temperature we measured in the cylinder with the thermocouple. You see that we have quite an hydration temperature in the mix. This means that this leads to thermal deformation. So we need to take this thermal deformation into account. So if you look at the right, that is in red what is measured by the sensor in terms of deformation. And in green is what we call the calculated shrinkage. The difference between the two is simply the thermal deformation. And you see that we have a very particular behavior for the early age deformation of UHPC. Typically, the first 24 hours after the production are really specific. So we can separate that in three different phases. First, the phase A. Typically, what happens during the phase A is mainly related to differences in temperature between the concrete and the ambient air. And you see that when we subtract the thermal deformation, the shrinkage is almost zero. Then in phase B, we have a huge increase of the shrinkage happening in the phase B. And then what happens there? There's a switch between the plastic state that we had in the phase A and a state where the plastic arrangements are impeded by the increasing stiffness of the matrix. And finally, in phase C, we have a slight swelling followed by a shrinkage, but at a much lower pace than in phase B. So during those three phases, we have a coefficient of thermal expansion that is not always constant. It is constant in phase A. It's a linear function of time in phase B, and it's constant as well in phase C. So what happened when we put the specimen at a relative humidity of 100%, typically in a fog room? We see that no matter the time at which we start the curing, we see that we have a slight increase of the shrinkage in phase B. Slight increase, but more interesting is that we see we have a significant reduction of the shrinkage rate in phase C, as well as the swelling observed at the beginning of the phase C that is increased when we have a relative humidity of 100%. So the increase in shrinkage is compensated by the swelling, and the shrinkage rate in phase C is reduced compared to the relative humidity of 50%. But even more interesting is what happens when we immerse the specimen in water. First, we see that we have an immediate swelling following the immersion. For example, we can see here, if we immerse the specimen at 9 hours or at 21 hours, we see that we have an immediate swelling following the immersion. And even more interesting is that the shrinkage in phase B when the specimen is immersed in water is reduced by up to 40%. So when we combine the effect of the swelling and the reduced shrinkage, we have a very effective way in mitigating the deformation when the specimen is immersed at 9 hours. And we see at 7 days a reduction of shrinkage up to 65%, which is really significant. Finally, when we use shrinkage reducing admixtures, remember SRA1 is supplied in the liquid form, so it's added after water and admixtures in the mix. SRA2 is supplied in a solid form, so it's added with all the dry materials before water and admixtures in the mix. And we see that SRA1 in the liquid form is much more efficient in reducing shrinkage than SRA2. It leads to a reduction of almost 70% at 7 days for SRA1. So really much more efficient than the SRA supplied in the solid form. So what are the conclusions we can draw from this experimental program? First, we've demonstrated that there is a major importance of the early age behavior, as more than 50% of the 28-day shrinkage occurs during its first 24 hours of maturity. That is significant. Another interesting conclusion is the major impact of the environmental conditions. We've seen that we can reduce the shrinkage by about 20% when the concrete is at a relative humidity of 100%, meaning in a fog room. But we've seen that immerging the specimen in water provides a reduction of shrinkage up to 65%, which is really much more efficient than just having a relative humidity of 100%. And finally, the immersion time is optimum just before the phase B starts. And for the SRA, we've seen that when it's supplied in a liquid form and added after water and admixtures, it helps in reducing the shrinkage by almost 70% at 7 days, while when we add the same materials in a solid form, it helps in reducing the shrinkage by a little bit more than 40%. So this brings information really interesting for the industrial use of UHPFRC. First, the fog curing might not be really adequate. We've seen that immerging the specimen in water is much more efficient. So maybe we should think about using sprinklers, for example, to apply that information for industrial use. Another thing is that we've seen that the starting time for water curing is optimum just before the phase B starts. So if you want to control the best we can the shrinkage, and especially the early age shrinkage, we need to control the starting time for the curing. And for the polyol-based shrinkage reducing admixtures, we've seen that we have a better shrinkage reduction when we add those materials in a liquid form after water and admixtures, rather than the same shrinkage reducing admixture in a solid form added with raw materials before water and admixtures. So finally, if we combined the reduction in shrinkage provided by the SRA and optimum curing conditions, then definitely it will help in minimizing the cracking due to restrained shrinkage. So we'd like to thank the Canadian Society of Civil Engineering for allowing us to present these results in the conference. We'd like to thank Polytechnique Montreal and especially Nicolas Boutin and the technical staff of the structural laboratory for helping us in the realization of this experimental program. And finally, we'd like to thank CRH Canada and the CLEAT Canada for providing us with the raw materials. So I thank you very much, and I'll see you in the Q&A event.